This is video 8.1 on torque. Torque is a quantity that measures the ability of a force to rotate an object around some axis. So here in an example, we have a merry-go-round. I want you to imagine that you've got a merry-go-round and that you pull on the merry-go-round along a radius. If you were to do this, if you were to pull along that radius, you would not get any rotation at all. Now consider this situation. If you pull at least partly perpendicular to the radius or partially tangent to the circle, then you will get some rotation in this second example, B. So in order to create torque, we have to have a force that is at least has a component that is perpendicular to the radius or tangent to the circle. The lever arm is the distance from the axis of rotation to that line of force. And that lever arm is sometimes called r sine theta. When we multiply F times r sine theta, then again we get torque. This funny looking T is actually a Greek letter tau, a lowercase Greek letter tau, and again that's torque. A positive torque indicates a counterclockwise motion. Just like on the unit circle, if you go counterclockwise, that's positive. A negative torque indicates a clockwise motion. And the unit for torque is the Newton meter. This is not a joule. It's a Newton times a meter, and that's because the situation is different than the situation that creates work. This situation is always all about rotation. So now what we really have here is we have a third condition for equilibrium. If you recall what we were studying earlier in the year, we looked at situations where objects could accelerate in a straight line. And in order to accelerate in a straight line, they would have a net force on them. So now we see that there are multiple ways that an object can accelerate. It can accelerate in a line, in a linear fashion, or it can rotate. So that's basically what these conditions are saying. An object is said to be in static equilibrium if both its velocity and angular velocity are zero or constant. And it has to be in translational equilibrium. That means the net force must be zero. And then also it must be in rotational equilibrium, meaning that the net torque must be zero. And if it meets those two conditions, then we say that the object is in equilibrium. Let's look at this force diagram for a sawhorse. So, looking here at this diagram, if I consider a sawhorse with a ladder on top of it, so here's the sawhorses, here's the ladder, and I can draw two different kinds of diagrams. I can draw a force diagram, and I can draw a torque diagram. Now for the force diagram, I simply draw the forces where they exist. FA, this upward force, is caused by sawhorse A. FB, this upward force, is caused by sawhorse B. And then FG is the weight of the sawhorse, and that weight is at the center of gravity. So this point right here, that's the center of gravity of the sawhorse. And basically I'm taking the ladder. I'm taking the whole ladder and sort of averaging it and saying, hey, the whole ladder basically is acting right there at that center of gravity. With a torque diagram, we do the same thing. We have to look at the forces, but then we also add, now we know we need to include their distance from the axis of rotation. So what I can do when I draw a torque diagram is I can pick the axis of rotation to be anywhere. And what I usually do is I pick the axis of rotation to be at one of the forces. The reason I do that is that then that torque disappears, because if the distance is zero, then F times R is zero. So let's say this dot is the axis of rotation, then I would have a torque due to the weight of the ladder, and then I would also have a torque due to this other sawhorse. So next, let's look at some practice problems. And I've just gone ahead and written out the answers here, and I'll kind of talk through them. So number one, A force is applied to the end of the lever shown, perpendicular to the lever. Find the force required to cause rotational equilibrium. Okay, so when I solve a problem like this, what I'd like to do is identify the pivot. And so the pivot is right here. And then I also need to identify the force, which is 15 newtons, and its distance from the pivot. And then you'll also notice I need the angle, which is 40 degrees, between F and R. So I'm going to use the formula, which is that torque equals R sine theta, and I have all those values. So F was 15, R was 1.5, and then I've got the sine of 40 degrees. Notice that the sine of 40 degrees would give me this vertical value, this component of the force that is perpendicular to the lever. And when I multiply that out, I get 14.5 Newton meters. So that's how much torque there is. But now the question is, what force is required to create rotational equilibrium? Well, this is an ambiguous problem because the question is where. So I'm going to have to make an assumption here. If I assume that the force is going to act at 1.5 meters in the middle here, then the torque needed would be 9.6, because 9.6 times 1.5 is 14.5. Or if the force were acting at the end of the lever, say at 3 meters, then 3 times 4.8 would give me 14.5 Newton meters. So in that case, the force would be 4.8 newtons. So again, if the force is out here, it'd be 4.8. And if it's at the center of the rod, the force needed would be 9.6. And your teacher should probably write a less ambiguous problem that doesn't make you ask, well, where, Miss Howell? Okay, let's look at another example. Number 2. Give me a lever long enough and I will move the earth. Suppose you weigh 735 newtons, or 75 kilograms. Suppose the earth weighs 5.87 times 10 to the 25th newtons. If you wanted to lift the earth with a lever arm of 1 centimeter by standing on the lever, how long would the lever have to be? So I've set this up so that the two torques are equal. So we've got a torque on the left here due to the person, 735 newtons, and the distance of the person from the lever is going to be R. And then we've got the earth, the mass of the earth, which is the 5.87 times 10 to the 25th, and then the earth's distance to the lever was just 0.01 meters. So I set it up in the formula and I solve for R, and I get 7.98 times 10 to the 20th meters, which is a very, very, very long lever. Now, what this person actually said, and it was Archimedes, what he actually said was, give me a lever long enough and a place to stand and I will move the earth. Because the faulty assumption here is that you can't use a lever to move the earth in empty space because there's no place to put the pivot. That'll slow you down a little bit. Okay, moving on to our next page. Let's look at some more examples. Explain the design of a door in terms of torque. And then how about the doorknob? So first we're going to look at these top 3 pictures. And I want you to imagine that you try to open a door by pushing right near the hinges. And when you push right near the hinges, you have almost no effect on the door because your lever arm, your R, is almost 0. If you were to push in the center of the door, it would be much, much easier to open the door, but not as easy as if you push at the end. Here, your lever arm is maximized. It's the biggest it can be. So the doorknob is positioned as far away from the hinges in order to maximize the torque, because you are maximizing R. This is assuming that the force that you exert in all 3 cases is the same. Here's another scenario. what if you have a door and you pull on the doorknob and you just pull straight out away from the door? My kids do this sometimes. They'll hang on the doorknob. Well, that's not going to turn the door at all. In order to turn the door, at least some component of your force has to be perpendicular. And pushing out, straight out from the door, perpendicular to the door would be best. Another thing to consider is how a doorknob works itself. Here we've been looking, in these pictures here, we're just looking at the doors. But think about the doorknob itself. In a round doorknob, a standard doorknob, there is torque. You're exerting torque around the outside of the doorknob, and the radius of the doorknob is your lever arm. In our school, we have lots of these lever-style doorknobs where the lever arm is actually larger, and that makes it easier to open the door. Let's look at example 5. We've got a 40-kilogram child and a 30-kilogram child sitting on either end of a 2-meter seesaw. Where along the seesaw should the pivot point be located in order to produce rotational equilibrium? Ignore the mass of the seesaw. Okay, so first I'm going to draw a picture. I've got my 40-kilogram kid over here. I've got the seesaw 35-kilogram kid over here. I'm going to call the distance on the left x, and I'm going to call the distance on the right 2 minus x, because the entire length of the seesaw is 2 meters. We've seen this technique before. And then I'm going to use equilibrium to solve this. So the torque on the left is the force, which is basically the weight of the kid times the distance to the pivot. And then the same thing on the right. The weight of the kid, which is 30 times 9.81, times the distance to the pivot. Weight of kid, distance to pivot. And now it's just an algebra problem. I actually went ahead and canceled out the 9.81s because it turns out as long as we're all on the same planet, it doesn't matter. So 40x equals 30 minus 2x. I distribute the 30. 40x equals 60 minus 30x. I'm going to add 30x to both sides so that I get 70x equals 60. So x equals 6/7 or 0.86 meters from the 40-kilogram child. Question 6. A 23-kilogram child now sits 0.2 meters from the 40-kilogram child. So in this scenario, we're actually taking a third child and placing them on the seesaw. And their distance, let's see, we found out that x was 0.86. And these kids are 0.2 meters away, which tells me that the distance from this third kid to the pivot is 0.66 meters. So now to find the net torque, again, I'm going to take the weight times the distance, and I get 148.9 Newton meters. And the direction of this, adding this kid on the left side, is going to produce a counterclockwise torque, which is a positive torque on my diagram. Okay. One more example. Suppose we do not ignore the mass of the seesaw in the torque problem. A 20-kilogram seesaw is 4 meters long. The pivot is 1.5 meters from one end. What is the net torque on the seesaw? So there's a couple of different ways that you can solve this. In this scenario, what I did was I first found the mass. I found the mass per meter. So I figured out that the seesaw is 5 kilograms per meter. And then I figured out that the left side of the seesaw must weigh or have a mass of 7.5 kilograms, and the right side of the seesaw must have a mass of 12.5 kilograms. And then I figured out the net torque by calculating the clockwise torque on the right side and the counterclockwise torque on the left side, and I wound up with my net torque, which was negative 98 Newton meters. There's actually a simpler way to solve this, and I'm going to try to do that now. What we can do is I'll redraw the problem. And the pivot. And the pivot is, it said 1.5 meters from one end, so this is 1.5, okay? And we know that the whole seesaw is 4 meters long. And now what we're going to do is we're just going to boil this down to just one torque, which is one of the things I love about physics, is being able to simplify things to their very core. So this teeter-totter is, or seesaw, is 20 kilograms and it's 4 meters long. So I've got 20 kilograms times 9.81 really just acting right here at 2 meters. And this distance then would be 0.5 meters away from the pivot. So to find the net torque, that's really all I need to do is take, is to pick a pivot, find the center of gravity of the whole darn seesaw, and then use the torque equation to solve. So I would say that the torque is equal to 20 kilograms times 9.81 times 0.5, and then the sign of 90, because this angle between the force and the distance are 90. And that's 1, so I don't need to worry about that. And lo and behold, my answer is still 98.1 Newton meters. And then again, I would notice here that this is a clockwise torque, which means, did I actually mess up here? Oh no, that's right. Clockwise is negative. So my final answer is negative 98.1 Newton meters.